couple of chapters in Algebra 2 on polynomials. So today it should hopefully be a lot of review. There might be a little bit that's new, but mostly review. I have them. You can do that. Like, I post them every day. I just don't post them beforehand because I wait till I fill them in. So what we're going to talk about is we're going to talk about how we can find the degree of a polynomial, our leading coefficient of a polynomial, and what that tells us about our end behavior. So end behavior is what's describing our arrows. So does anyone remember what the degree of a polynomial is? I have it up here. The highest exponent. So our degree is our highest exponent. And it's our highest exponent if it's in standard form. So that means if it's fully multiplied out. Our leading coefficient is going to be what? What might the leading coefficient be? What is a coefficient? The number in front. So if it's our leading coefficient, what that's going to be is the number in front of that highest degree term. They're related to each other. The number in front of the highest degree term. And technically, polynomials are equations that have a degree of 2 or higher. I mean, technically it could be 0 and higher, but we don't ever call constants polynomials. So if we think about any sort of generic function, I'm just going to make one up right now. If I have f of x equals, let's go with 3x to the 4th plus 7. What is our degree? 4. What is our leading coefficient? 3. It's the number in front of the biggest exponent term. What that tells us is it actually tells us a lot about our arrows on our function if we were to graph it. So if we have even degreed functions, meaning parabolas or things to the 4th or things to the 6th, even degrees, what that tells me is that our ends are going to match. So parabolas look like this. They're U-shaped. If it was a 4th degree function, it might look like a W, but they're still both pointing up. If it's a 6th degree function, it'll have another squiggle, and then it'll still point up. So even degree functions have end behavior where they point the same direction. It could be that they have both pointing up or both pointing down. So it's going to match. And the way we can tell which direction that's going to go is we look at the positive or negativeness of that leading coefficient. If we have an even degree and a positive leading coefficient, that's when we're going to have up, up. So we would have arrows that look like this. But that's not how we're going to write things down. That's not how we notate it. When we're writing down our end behavior, we say as x approaches negative infinity, so as my x's get smaller and smaller and smaller, my function f of x, or g of x, or y, or whatever we have, approaches, it's going to go up, so it's going to approach positive infinity. And we need the other arrow too, because that just describes our left arrow. As x approaches positive infinity, so as x gets further and further to the right, our function, f of x, is going to approach positive infinity. This statement means, and I'm just going to write it in words here, this means left arrow up. This one means right arrow down, up. Excuse me. I'm good at talking. This means left arrow up, right arrow up. Both of them are pointing up. If we have that negative leading coefficient, so if I had a negative x squared, they would both point down. That's when we get that reflection. So what's going to be different in our end behavior for this one? It's going to go to negative infinity. The first 3/4 of it is exactly the same. As x approaches negative infinity, f of x approaches negative infinity. Or my left arrow goes down. That's what that means. As my x's get really, really small, my y's get really, really small. And we're going to write their other arrow down. As x approaches positive infinity, our f of x approaches, they're both pointing down, so this one's also going to be negative infinity. That's my right arrow down. So when we're looking at even degree functions, sometimes it helps to think about a parabola. We're very much comfortable with parabolas, whether it's a positive happy face parabola or a negative frowny face parabola. Pretty good with those. But that's only for our even degree functions. What if I don't have an even degree function, but I have an odd degree? Maybe 1, or 3, or 5, or 7. So even or odd degree functions follow the same end behavior of like lines or cubes if you're comfortable with cubes. But odd degreed functions are going to have arrows that point in opposite directions. Lines we're pretty comfortable with. And if we think about this in terms of things like slope, if I have a positive slope, it goes up like this. And if I have a negative slope, it goes down like that. So positive sloped functions have that same end behavior as odd degree functions with a positive leading coefficient. So the way we write that, we say as x approaches negative infinity, my f of x, or my function, approaches, it's going to go down on the left-hand side on this one. So it's going to approach negative infinity. That's my left arrow points down. And what's different with our odd degrees and our even degrees is the odds we're going to have point in opposite directions. So as x approaches positive infinity, my f of x is going to approach positive infinity. It's my right arrow up. And you do not have to like write the pink down for an answer. That's just me putting it into words that we're more comfortable saying. My right arrow points up. One more set of end behavior for this page. We've got our negative leading coefficient on our odd degree functions. So that would be if we have a slope with a negative, or a line with a negative slope, it would have that same end behavior. So we're going to have as x approaches negative infinity, what does my f of x approach? Positive infinity. Absolutely right. Good. Again, that's my left arrow is going up on this one. And so my x approaching positive infinity, my f of x approaches negative infinity. Right arrow down. I just like to put it in words like we normally say, just because I feel like that does help. When we're writing end behavior, it doesn't necessarily matter if you put your x approaching negative infinity first, or x approaching positive infinity second. It doesn't have to be that way. I tend to do that because we read from left to right, so I start on the left and I go to the right. It also then keeps things fairly consistent, so that if we're not sure what's happening, I'm trying to keep things easy to understand. So it doesn't matter to me if you put your positive infinity over your negative infinity. Just be really careful and intentional with it. But it doesn't matter what order we do it in. I just tend to go from left to right just to keep everything consistent. And that's the way we read stuff. So questions on this giant list of end behavior here? There's a lot. Okay, let's take a look at this little squiggly graph over here. We're not going to do much with it, but I want you to look at this and see if we can figure out what kind of degree this might, or what kind of, degree it might have. It's going to be an even degree function, because both arrows point up. Is it going to be positive or negative leading coefficient? Positive, because they're both up. And I heard someone had an idea about what our degree might be. 6. Why? Because it changes directions 6 times. So it goes 1, 2, 3, 4, 5, 6. Changing direction. That increasing versus decreasing. We can also look at how many roots it has. This one has 5 roots, but we know it's going to be an even degree function, so it has to be at least 6 of our degree. And we're going to be looking at a lot of those pieces as we go through the rest of the day. We're not going to do much with this picture aside from that. Just looking at them and reading them. Okay, questions on what's up here before I change the page, because I know this is a giant wall of text. Because what we're going to start with is I'm going to give us an equation. We're going to find our degree, our leading coefficient, our end behavior, and a couple other little pieces. One other little piece. So this is 2 different equations here. I'm going to put a little barrier just so we don't get mixy. So this is. So we're going to start with our f of x, which is 5x to the 4th plus 3x squared minus x plus 1. All right, my first question is, what's our degree? Say it again. 4. Our biggest exponent is our degree. So our degree is 4. What is our leading coefficient? 5. Made me think real hard. Start tossing it out in other languages. Whew. From that alone, we can get our end behavior. I have a degree of 4 and a leading coefficient of 5. So are we going to be even or odd? Even. And are we positive or are we negative? Positive. Because that's a positive 5. So even and positive, I know my end behavior for that. We just wrote that down. That means it's going to be the same end behavior as a happy face parabola. So as x approaches negative infinity, what does f of x approach? Positive infinity. My left arrow points up. As x approaches positive infinity, what does f of x approach? Positive infinity again. It's even. They're going to match. I'm going to make this top one just a little bit bigger because I feel like it's very small. So my last question up here, I'm going to go back up to it, is my y-intercept. Where might we have a y-intercept?
X equals 0.
Not x equals 1. Because my x is 0 because it's a y-intercept. So 0, comma 1. It's always, always, always going to be whatever your constant is here. Because if x is 0, 5 times 0 to the 4th, 0. 3 times 0 squared, 0. Minus 0, 0. Plus 1. So our y-intercept is going to happen where that constant is at the point 0, comma 1. So even without knowing anything else about this, I know where my arrows are pointing. They're both pointing up. I know where my y-intercept is. And I know we're going to have some little squiggles in there. We're going to do the same thing for the next one. Now we're going to look at g of x, which is my negative 2x to the 5th minus x cubed plus x squared minus 4. Same process. What is my degree? 5. My biggest exponent. Which means what is my leading coefficient? Negative 2. So are we even or odd? Odd. And are we positive or negative? Negative. So odd and negative, there we go, I'm good at spelling. We can do our end behavior then. So as x approaches negative infinity, what's going to happen to my g of x? Be careful. I heard both. Think about our odds and negative. Think about a line with a negative slope. So our g of x is going to approach positive infinity. Whenever we have odds and negatives, think about a line with that slope. Odds have the same end behavior as lines. So as x approaches positive infinity, what's going to happen to g of x? G of x approaches negative infinity because my right arrow points down. So it has that same end behavior as a line. And then our last piece up here, where's our y-intercept going to be? At 0, negative 4. This guy is my y-intercept. So it's at the point 0, comma, negative 4. And it is a good habit to be in to always write our intercepts as ordered pairs. It's a good habit. I'm not going to be petty about it, but it's a good habit. Okay. This should hopefully be reviewed, but I know it's been a hot minute. Questions on these ones? Because this works all well and good when I give you something in standard form. What about if I give us in factored form? We're going to make ourselves a little bitty sketch to go with it, too. Oh, snap. It's not a proper graph. We're going to sketch. So that's why I'm not going to pass out graphs. We're just going to sketch it. So I have 3 times quantity x plus 2 squared times x minus 4. So, trying to find our degree first. If we were in standard form, it would be our biggest exponent. say this one's not in standard form, so how many x's would be multiplied together? 3. So we have, and I'm going to grab a highlighter real quick. We have x squared, so there's 2 x's, times another x. So that tells me our degree is going to be 3. What is our leading coefficient going to be? This guy right here, out in front. So our leading coefficient is 3. So even just from that, I can get my end behavior. I don't need to look at anything else to find my end behavior. So we have what, even or odd? Odd. Are we positive or negative? Positive. So as x approaches negative infinity, thinking about odd positives, what is going to happen to my f of x? F of x approaches negative infinity. Think about our lines with a positive slope. As x approaches positive infinity, what happens to f of x? Approaches positive infinity. What that tells me is no matter what happens in the middle of my graph, I know my left arrow is going to point down and my right arrow is going to point up. So now this part's going to be some review and see what we remember. Where are we going to have zeros? At -2 and positive, what? 4. So I'm going to have a root at -2 and a root at positive 4. When we're sketching, that's all we need to do with that part. Now, the trickiest one up here is to try and figure out what our y-intercept would be. If we were to multiply everything out and put it in standard form, we could, but that's a lot of work for figuring out our y-intercept. Because what we need to do to find our y-intercept is to multiply all of the constants, all of the numbers. So we're going to take our leading coefficient, that 3 from out in front, times our 2, that is being squared, it's inside the square, times our -4. So we have 3, our leading coefficient, times 2, times -4. Our y-intercept is going to be at -48. So it's the point 0, -48. Which means when I go to my little sketch, I'm just going to put it down here and just label it -48. We don't have to do it. That's why I didn't pass out graphs. I was like, we're not doing this to scale. Sketch. We're getting the vibe. So now we need to connect these up. My left arrow points down. I need to hit that -2. I need to go through -48. I need to come up through 4 and not have any extra x-intercepts. So when we connect these up, changing my color real quick. There we go. I tend to start at the left and go to the right, just because, again, that's how we read graphs. So I'm going to come up here. I'm going to bounce off that -2. I'm going to go through my -48. I'm going to come up through my 4, all the way up to my other arrow. Another way that you can tell we're going to bounce off a root, if we have a factor that's being squared, that means we're going to bounce off it. That's called a double root, or the multiplicity. Remember that? It's been a hot minute since we did multiplicity. It'll come back. So we're getting as much information as we can off of this, and at this point, this is what we can get. Okay? Questions on this one? Yes questions or no questions? Cool. All right. We're going to do it again. I know. I'm hard with girl. Doing it again. So we've got our f of x equals -2 quantity x plus 1, quantity x minus 3, quantity x plus 2 squared. Give me guys a second to write it down. So, first things first, what is our degree? I heard it, but it was quiet, and then we had several conversations. 4. So I have x times x times x squared. That's 4 x's. I'm just going to go down the line this time. Where are our zeros? -1, +3, and -2. What's special about our -2? It's going to be a double root, so we're going to bounce off of this one. And you can write that down if it helps you. You can also just deal with that later. It doesn't matter, genuinely. It's a double root there. What is our leading coefficient going to be? -2. What is our y-intercept going to be? We take all those constants. I'm going to take my -2 times my 1 times the -3 times the 2 squared. That's how we find that y-intercept. All the constant numbers. So -2 times 1 times -3, +6 times 2 squared, which is 4, gives us 24. So our end behavior is going to look like what? Are we even or odd? Even and negative. So as x approaches -infinity, f of x approaches -infinity. As x approaches +infinity, f of x approaches -infinity. So I know no matter what happens in the middle, my left arrow points down and my right arrow points down. So I'm going to plot my roots. So I know we have roots at -2, -1, and +3. And we have our y-intercept at 24. So the point 0, 24. So we need to make sure we hit all of our roots. And we go through our y-intercept. I'm just going to change the color on this -2 because we need to make sure we bounce off this one. That's our double root. So we're going to bounce off our -2 and then go through the -1, through the 24, through the 3. So we're going to go bounce off the -2, through the -1, through the 24, through the 3, down to my arrow. And these are sketches, so it doesn't have to match exactly. If you take your line and bring it like way down here, that's totally fine. If you make this really shallow, that's totally fine. If you add in extra wiggle squiggles here, that's totally fine. We're just not adding any other roots, and we're not adding any other intercepts anywhere. And it's got to still be a function. Okay, questions on our sketchy parts? Okay, just a smidge of that. I'm not going to do more sketches. We're going to tie in our next kind of theorem. It's going to be like proving things about polynomials. And it's going to be something called the intermediate value theorem. And it's got a very wordy definition right here. So we've got f as a polynomial. And we know that f of a is not the same as f of b. They don't equal each other. What that means is that somewhere between a and b, it hits everything in between. And the way we use this is if f of a, so my y value at a and my y value at b, if they have opposite signs, meaning one is positive and one is negative, then somewhere between a and b, there is a root. There is a 0. So you're going to be given problems in this first homework that say, prove that there is a root between 2 and 3. Prove there is a root between -4 and -5. And what we're going to do is we're going to substitute those values into our f of x to say, all right, one of these is positive, one of these is negative. That means there has to be a root in between. What we're saying, I'm going to give us a little sketch to show here. If I have a polynomial that looks like this, and I know that this is -3, has this value here, and I know that this guy is -2, which is this value here. Since f of -3 is negative, and f of +2, or f of -2 is positive, somewhere between -3 and -2, I have a root. That's what we're trying to prove. Trying to say that I know this guy has to exist. It might be decimally and gross, but this point exists. And that's what we're going to work with. So on these kinds of problems, they're going to give us an equation, an a and a b. So that's what I'm going to give you. Now we're just going to practice this a couple of times, and that's going to be it. So we're going to use the intermediate value theorem to prove that there's a root on this one between 3 and 4. So my f of x is x cubed minus 4x squared plus 3x minus 2. And we're looking at 3 and 4. So our first step is to find both f of a and f of b. So I know my a is 3. So this is really asking us for f of 3. So we're going to substitute that in. We're going to have our 3 cubed minus 4 times 3 squared plus 3 times 3 minus 2. And aren't we so happy to use calculators now? Imagine trying to do this without calculators. Last year they had to. So our f of 3 is going to equal what? -2. We'd have 27 minus 36 plus 9 minus 2. Or you can type the whole dang thing in the calculator and go from there. Okay, I'll write it down. So we got our 27 minus 36 plus 9 minus 2. You don't have to use a calculator. We can absolutely do this in our heads. Like, you can do it. Then we're going to look at f of b. So this is f of 4. So substituting into that same equation, we're going to have our 4 cubed minus 4 times 4 squared plus 3 times 4 minus 2. So our f of 4 is
10.
How'd you get 38?
I think it's 10.
How'd you get 38? I think we dropped a sign somewhere? Or like dropped an exponent? Because we should get, if you do it by hand, it's 64 minus 64 plus 12 minus 2. So we get 10. So I have that f of 3 is a negative value. F of 4 is a positive value. So the way we kind of state it, because this doesn't count as showing it, you did a whole bunch of work, but it didn't prove anything. Since our f of a is less than 0, because it's negative, and f of b is greater than 0, there must be a root. I'm going to put root on the next line. Between a and b. There has to be one. Because at f of 3, we are negative, and at f of 4, we are positive. It's got to cross the axis somewhere between them. So it has to hit 0. Okay? So it's a super complicated name, but not the worst calculatorily. We're going to do it again. That'll be the last one. All that would do is if these were switched, you would just switch which one has which inequality. Boop. This is the last one for the day.
Oh, that's
We can do this even with fractional roots. Or fractional a and b's. So my f of x is 2x to the 4th plus 3x minus 2. And we're looking between 1/2 and 3/4. Now, aren't you extra glad you can use the calculator? So we're going to start by finding our f of a and our f of b. So f of a, we're going to do our f of 1/2. That's going to be 2 times our 1/2 to the 4th plus 3 times 1/2 minus 2. If you're new to these yellow calculators, second column, third button down is your fraction button. It looks like a fraction. It behaves like a fraction. It looks like those are fraction things. And you can type it in just like that. 2 parentheses. Second column, third button down, fraction. 1/2. Close it to the 4th. Plus 3, open parentheses, times 1/2. Minus 2. So f of 1/2 is going to be what? Not -8. -3/8. We're going to do the same thing with our b of 3/4. F of b, that's my f of 3/4. So we're going to have our 2 times 3/4 to the 4th plus 3 times 3/4 minus 2. So our f of 3/4 equals I was going to say, it's going to be kind of gross and I don't have it simplified over here. So 113 over 128. Aren't you so glad you don't have to do this one without a calculator? Well, because we would just do 3 to the 4th over 4 to the 4th, times it by 2. So since my f of a is negative and my f of b is positive, this is our last line we write, guys. So since f of a is less than 0 and f of b is greater than 0, there must be a root between a and b. Okay? So that's all the way up to our intermediate value theorem, and tomorrow we're going to work with some more sketching stuff. Y'all got a minute and a half. For oh, they should be.